All right, this is a review of problem 2B.4. It's basically just a continuation of 2B.3 with one minor difference. So you might want to go back and watch that video for parts of it. It's basically just 2B3, but you change one boundary condition. So allowing the wall at x equals b to move in the positive y direction at a steady speed v0. So going back to 2B3, just going up and just looking at this whole thing. All this is in the previous video about 2B3. The only thing that you're changing here is the first boundary condition it's going to be at x equals plus b vz equals v0. So yeah, all the previous procedure is the same except at x equals plus b. Two boundary conditions at x equals negative b, vz equals 0, because obviously that wall is still not moving, and at x equals b, vz equals v0. So, I guess you only need to do these two boundary conditions. You don't need to do the derivative boundary condition, but the derivative boundary condition doesn't apply actually, because one of the walls is moving and the other one is not. So there's not going to be a point. The maximum velocity is not going to be directly in between them, so that previous boundary condition won't apply, where the tau xz equals 0 at x equals 0, that won't apply. So this is the double derivative equation that we found from the previous problem, which is this. So we're just integrating the same thing from the previous problem with new boundary conditions. So that's what we do. Separate and integrate. Dx goes to this side, and the integral of dx is x. So the integral of d this will just be this. And obviously you can see that there. On the other side, you just multiply the x, and you have the c1. You can put the c1 on either side. It doesn't matter. You only need one constant, because you could just add or subtract the constant to the other side, and it's the same as having one constant. So now we're going to isolate the derivative and integrate it again. We can't apply a boundary condition straight from here because we have no dvx dx. We have no... Both our boundary conditions are VZ boundary conditions. They're velocity boundary conditions. They're not shear stress boundary conditions, so we can't apply them when we just have a derivative. Integrating again, x squared divided by 2, multiply by x, add the second integration constant, and now we're applying the boundary conditions. This is the first boundary condition. At x equals negative b, vz equals 0. At x equals negative b, vz equals 0, so it's negative b squared. It's going to be b squared, vz equals 0, negative b, and then we just isolate c2 to solve for c2. We get this, and we get that in terms of c1, so we can just plug that in again. We could plug this in here, and then we'll only have... our only unknown will be c1 when we plug in the second boundary condition in. So here's this definition is c2 here, and we're just plugging it in here. So we only have one unknown, which is c1. And here's the positive b squared again from the initial boundary condition, or this boundary condition at x equals b. Positive b, vz equals v0, and vz equals v0, x equals b, x equals b. And we eliminate canceling terms here. We get negative c1b over viscosity equals v0. And so we need to isolate c1, so we can plug that into the velocity equation. And then we plug c1 back into the equation for c2, just to solve out this equation here. And we get C2 equals this. And now we can plug in C1 and C2 into the equation. And yes, so C2 and C1, we're plugging this in this equation here. So that's what we're doing there. Yeah, so that's what I did here. And some sign canceling, algebra stuff, more algebra stuff, and we get VZ equals this. And that matches, that should match 2B.4. Yeah, that matches. So now I got to backtrack because originally I didn't do the shear stress velocity at first. So we got to look back at the equation. Negative mu dvz dx equals the shear stress xc, and that's what it's wanting us to find. Tau xc. Tau xc. It's wanting us to find tau xc. So if you look at table B1, you can find the definition for tau xc. Table B1. Tau xc equals tau zx equals negative mu dvx dz plus dvz dx, and this term cancels because there's no x velocity, so it's just negative mu dvz dx. And we know this is the definition for that because we have, where is it? This equation here from our first integration, dvz dx equals this, and we plug in C1 to that. We plug in, where's C1? C1. Plug in C1 and I mean, yeah, you could just use this equation too because this is the exact form. So yeah, just plug in C1 here, and that's going to be the shear stress tau xc. Yeah, so that's what I did. Equals this, and then plug in C1, and then you get tau xc equals that. And that is the same as the answer there. So that's good. It means we did it right. All right, so now it asks, draw carefully labeled sketches of these functions. I just did it in Desmos. This is velocity, and this is the shear stress. So yeah, this is just P0 minus PL, or P represents P0 minus PL over L. U represents viscosity, and V represents V0, and everything else is pretty self-explanatory, so I guess I could just mess around with this. Yeah, well, okay, U, or viscosity, you're changing it. Velocity, you're changing it. That's what it does, obviously. Wow. Let's see what it does when it goes in the opposite direction of velocity. Oh, it just goes over the line. Pressure, I think it should do somewhere. Oh, maybe it didn't get. Ooh, that's kind of interesting. Huh. Let's change the distance between the plates. Whoa. Interesting. Oh, it converts. At 0, it's just nothing. Okay, yep, that's the problem. Have a nice day. Bye.